Okay, so how y'all feel about tomorrow being May 1st? And the Add Maths exam being 3 weeks from today? Anyhow? No how? No comments?
I think about it.
Living in denial?
Yes.
It's like coming to an end.
Yeah, yeah. Well, every new beginning comes from some other beginning's end. Anybody knows that song? There's a song called Closing Time by Semisonic. Anyhow, yeah, y'all might know that one. Alright, so today we wanted to do some trig identities because we said that was one that was giving some trouble, right? Okay, so we're taking the exercise from the yellow and green book, the usual one that we used last time. So what I'm going to do, I'm not going to go over the derivations of the identities. I'm just going to go to the identities and a couple of the tricks that we have to know in order to be able to tackle these things properly, right? Okay, so once again, pardon the handwriting. Alright, so trig identities. Good boy, bad today. So identities in this particular incidence come from the word identical, not identical, right? And what does identical mean? The same as, right? So what's going to happen is we're going to have one thing, one expression, and it's going to be equal to another expression, and we have to convert it from one form to the next, all right? So okay, so let's just recap the basic trig ratio, shall we? So sine is equal to, sorry, not sine. Right, first identity we should know is sine squared theta plus cos squared theta is equal to 1. Right, that is the basis from which all the others are derived, except for one other item. And that one is that sine theta divided by cos theta is equal to tan theta, right? Once you know these, you basically know how to get the rest. But there's also now the thing is the inverted trig ratios are not officially on your syllabus, sec, cosec, and cotan, but I go through them anyway because, I mean, the book does not omit them. I'm not working from that other purple book because I don't like it. All right, cool, and don't forget, right, so like I was saying, the inverted trig ratios, sorry. All right, so inverted trig ratios. Right, so 1 over sine theta is equal to cosec theta. 1 over cos theta is equal to sec theta. And 1 over tan theta is equal to cot theta. And remember, tan is sine over cos. So if you put 1 over tan, you have to invert that fraction. So that's cos theta over sine theta. This is going to be one that's kind of important in some aspects. I mean, they're all important, right? Sorry, I don't know what's going on with my throat. All right, so let's take a look and see what happens when we basically use these inversions inside of here. All right, so what we're going to do, let's start with 3. So let's do sine squared theta plus cos squared theta equal to 1, and we are going to divide everything on both sides of the equation by cos squared theta. So cos squared theta here, cos squared theta here, and cos squared theta there. All right, so from here we know that sine theta over cos theta is tan theta, so sine squared over cos squared will give us what? Tan squared. So that's tan squared theta. Cos squared, anything divided by itself will give us back 1, and 1 over cos is sec. So 1 over cos squared is sec squared. All right. Alternatively, if instead of dividing everything by cos squared, we divide it by sine squared, let's see what would happen there. All right, so we have cos squared theta equal to 1, and everything is being divided by sine squared theta. Sorry, I need to put this way. That might be a little more helpful. All right, cool. So sine squared over sine squared is what? 1. Cos squared over sine squared. So tied to that, what's cos over sine? That's 1 over tan, which is cot, and cos squared over sine squared will give us cot squared. 1 over sine is cosec, so 1 over sine squared is cosec squared. Yes? No? Maybe? All right. So it is from this batch of stuff here that you're going to be using these things to do all of the identities, right? There are no other things that you'll have to know in terms of the trig identities or ratios to be able to do any identities that come your way. Sorry, that's not entirely true. There are items such as the double and multiple angle expansions like sine of a plus b cos of a plus b or sine of 2a cos of 2a. I don't know if we'll get there today. Like I was saying, this is not a one session topic. Even if you're recapping, you should probably do these first and then do those identities on next day, right? So we'll figure it out. All right, now a couple of tricks you should know when you're dealing with the identities. We do, a lot of times there's some fraction questions and you have to know how to decompose fractions. A lot of times you'll find difference of 2 squares. So let's just jot that down. So fractions, right? Addition, subtraction, decomposing. Now what I mean by decomposing a fraction, for example, let's say you had x plus 2 all over 3. You can express each of the items in the numerator over the common denominator. Right? So that's what decomposing a fraction means, right? If you guys go on to do pure math, you'll do something called partial fractions. That's real fun, all right? Of course, you know my definition might be a bit different from yours, but nonetheless, right? So fractions, addition, subtractions, decomposing. There's one I like to call a double inversion. Right? So the example here is, let's say you had 3 over x plus 2. Right? So what you could do here is you can't decompose this as, in any case, there's just one item in the numerator, so you can't really decompose it anyway, right? But if we were able to flip this, right, by putting 1 over it. But you see, the thing is, 3 over x plus 2 is not equal to 1 over that. So what you do is you invert it again. So that's why I call it a double inversion, because when we're in this form now, what happens is that this piece here becomes x plus 2 over 3. And you can split that, right? So you'll get 1 over x plus 3 plus 2 over 3. Right? Now, I'm not saying that this is a usable form, but in certain instances, that might be what you have to do in order to progress any question. Right? Of course, we have algebra, algebraic identities, right? Such as a plus b all squared. So what's the expansion of that perfect square? A squared plus 2ab plus b squared. What about a minus b all squared? That's a squared minus 2ab plus b squared. And of course, the ever popular difference of 2 squares. Now, most times they won't give you in this form. They will give you in this form, and you have to be able to work backwards. Now, I'm not saying it'll never appear like this, right? It quite possibly can. And the thing is, you have to be able to recognize that a squared minus b squared is not the only form of difference of 2 squares. You can have, for example, a to the 4th minus b to the 4th. That is also a difference of 2 squares. It looks like a difference of 2 quarts, right? Because, well, the quartic powers, right? But isn't a to the 4th a squared squared? There you go. So you could actually factorize this as a squared plus b squared by a squared minus b squared. All right? So you need to there are a lot of things you have to bear in mind. And when I was prepping this topic for you all last year, it was around that time, I was working from some of the newer pure math textbooks. Honestly, most of the questions were very doable once you're comfortable, even to a medium extent, not necessarily advanced extent. There were 3 questions I remember that I took a couple sides of a page to work, right? And usually when that happens, there's usually always a shorter way to work it, all right? But yeah, we can have some challenging ones, but we got to start somewhere, right? Okay, so with this stuff, anybody wants this page printed out? Are we okay? Good? All right, cool. All right, cool. All right, so we're taking a look at example 14. All right, example 14 from page 145. All right, so we have cot theta plus tan theta, triple equal sign, which means identical to, and this is cosec theta by sec theta, right? Now, usually what you do, you take one side and you work your way towards the next side, all right? So sometimes people insist you put your statements, so I'll just show you that for good measure, right? So we are, what you could say is you are required to show that cot theta plus tan theta is equal to that, and then you put proof, all right, as follows, all right? And you could put taking, now to me, the left-hand side usually has more meat, well, meat, right? So what we could do here, all right, so cot theta is what? That's 1 over tan, or what was the alternative form for that? All right, right, so we have cot theta plus tan theta. All right, so you could do cos theta over sine theta plus sine theta over cos theta. All right, simple fractions here. With addition of fractions, what do we need? A common what? Denominator. What would be the LCM between sine theta and cos theta? Well, sine theta cos theta. Yeah, I agree with that. Now, let's shift it below. So, all right, so we have sine theta. So sine theta into that goes cos theta times, if you multiply that by the numerator now, we get what? Cos theta by cos theta is cos squared theta. Similarly, cos theta into that denominator will give us back sine theta. And sine theta by sine theta will give us sine squared theta. And from our primary identity, the sum of sine squared and cos squared will give us, sorry, what was that? 1. There you go. Thank you. Sine theta. So now we have 1 over sine theta cos theta. And we could decompose this, so just simply break it up very simply into 1 over sine theta by 1 over cos theta. 1 over sine theta is equal to cosec theta. 1 over cos is sec theta. Right, and you could put QED, which is Latin for quad, well, I think it's quad erat demonstratum or demonstratum, and it means basically what was required was shown, or some people say quite easily done, or some people just put a bit of a square, rectangle-ish kind of thing. Up to you, your choice. Okay, any questions on that item? No? All right. Let's take a look at example 15 one time. Oh, wait. All right, sorry. Okay, so example 15. So it says show that. So we are required to show 1 over 1 plus sine theta plus 1 over 1 minus sine theta is identical to 2 by sec squared theta. All right, now notice we have a 1 plus sine theta and a 1 minus sine theta, and it's a fraction, right? We have two, those are the denominators of two separate fractions, and we're adding them. When we're adding fractions, what's the protocol? What we have to do with the denominators? Find an LCM. So the LCM here would simply be the product of those two things, not so? So if you want, you could start off by showing you have your 1 plus sine theta, sorry, not plus, multiplied by 1 minus sine theta. And same thing, 1 plus sine theta into that denominator will give us back 1 minus sine theta, multiplied by 1 will give us 1 minus sine theta. Yes? Similarly, 1 minus sine theta into that denominator will give us, sorry, right, will give us 1 plus sine theta. And multiply that by 1, we're going to get what? Just 1 plus sine theta. Now, here, 1 plus 1 will give us what? That'll give us 2. Minus sine theta plus sine theta will cancel to 0, I think, yeah? Now here, difference of two squares, what would that give us? 1 plus sine theta by 1 minus sine theta will give us a squared minus b squared, right? So 1 minus sine squared theta. Aha! And according to our primary identity, of sine squared plus cos squared is 1, if you were to carry sine squared over and have 1 minus sine squared, what would that be equal to? That would be equal to cos squared, 2 over cos squared theta. And according to our inversion, 1 over cos is sec. Alright, which means therefore, so here we have 2 over 1 multiplied by 1 over cos squared. Now this is just for illustrative purposes. So that's 2 multiplied by sec squared theta. Q, E, D. Yeah? Alright, cool. Sorry, I'm just trying to grab something. Okay, and one example for the road, and then we're going to tackle some, you guys are going to try some questions. Alright? I will do any and all solutions. You all need me to on the board. Alright? But I want you all to do some lifting. Alright? Some mental lifting. Alright. So if we turn the page, example 16, so we are required to show, or some people RTP required to prove, alright, that we have tan squared theta is identical to sine squared theta by 1 plus tan squared theta. Now in this particular case, I think the right hand side may have some more meat. Alright? So proof. Alright, taking the right hand side. So we have sine squared theta by 1 plus tan squared theta. Now before you jump in and start to apply the distributive law and multiply sine by 1 and sine by tan squared, now I'm not saying that something is wrong with that, but saying before that, if we look back at our identities and we look at this item here, isn't that tan squared plus 1 or 1 plus tan squared? And what does that give us? Sec squared. So we could convert this very simply to what? Sine squared theta multiplied by sec squared theta. And we know that 1 over cosine is sec, not so? Oops, sorry. Right. So if you have sec squared, that's equivalent to what? 1 over cos squared. So we have sine squared theta multiplied by 1 over cos squared theta, which will simply give us sine squared theta over cos squared theta, which will give us tan squared theta. QED. Right. If you want to custom write any statement parts, don't worry about them too much. I'm not looking to try to disrupt the equilibrium at this particular stage, right? Now, the exercise, anybody have any questions on the ones we did? Now, just remember your process. The process is the important, the analysis, the application of what you know, right? All I did was I used these particular items here, right? But of course, the more you practice it and the more you look at these things and write them down is the better chance you'll have of remembering. Now, you will have some of these identities on the formula sheet on the paper, but I don't like to depend on them to supply those things because sometimes there are errors. I'm not saying there will be. I'm just saying I rather know what I have to use. All right? Anyhow, okay. Just I'm hot from out and do my work, right? So we have sine theta by cot theta is identical to cos theta. Okay, so what do we remember about cot theta? That's 1 over tan, right? And another way to write that is equal to what? Cos theta over sine theta, right? Cos theta, sorry, not equals, my bad, right? Over sine theta. And then what's going to happen there? Sine will cancel with sine, giving us cos theta. All right? So, not too much needed there, but once again, there are different ways to get that answer. All right, the next one we have 1 plus, so we have tan squared theta multiplied by cos squared theta is identical to 1. All right, now from our original things, 1 plus tan squared was sec squared. And 1 over cos is sec. So first things first, this will be sec squared theta multiplied by cos squared theta. Sec squared theta is 1 over cos squared theta. And that's multiplied by cos squared theta, which means what? Cos squared will cancel with cos squared, giving us 1. Alright, so far so good? Yeah? Yeah? Alright, cool. Going again. Number 3. So we have 1 plus tan squared theta by 1 minus sine squared theta is again identical to 1. Now, when I was in Form 4, Form 5, for some reason I did not realize that I did not know about, sorry, not this page, these, why does it not scroll? Alright, I did not know about these identities, right, which would actually make solving this one very easy, because 1 plus tan squared, if you look from above, 1 plus tan squared is what? Sec squared, right? And 1 minus sine squared is cos squared. And this turns out to be the same problem from above. So we just end up with, once again, 1 over cos squared theta multiplied by cos squared theta. That will cancel with itself, giving us 1. Alright, so could you imagine expanding that using distributive law and then simplifying it? Well, I did. And I didn't have to. Okay, here we have cos squared theta minus sine squared theta, and that's identical to 1 minus 2 sine squared. Alright, so whenever you have cos squared and sine squared, we usually kind of gravitate towards using this, but here it's sine squared plus cos squared. But the thing is, if we notice here, we only have sine squared and not cos squared. So we could actually use, sine squared plus cos squared, right? So remember, if you have, sorry, I don't know what's going on with my handwriting today. Alright, so you have sine squared theta plus cos squared theta equal to 1. And if you transpose to make cos squared the subject of the formula, we get 1 minus sine squared. So we have 1 minus sine squared minus sine squared, right? And minus sine squared will give us what? Minus 2 sine squared theta. Alright. Okay, so you guys, it's actually set up to number 4. So, the number 5? Okay, cool. Alright, any questions on anything so far? 1, 2, or 3? 1, 2, 3, or 4? Are we okay with that? Yeah? Alright. Question?
For number 4, I was trying to do the
Difference of 2 squares?
yeah.
Yeah, I did that initially too, and I was like, I can't go anywhere with this. Yeah, because you will get cos theta plus sine theta by cos theta minus sine theta. And I'm like, can't really go anywhere. Because it would force it to go back to combining it. Anyhow, number 5. Okay, we have sec theta minus cos theta is identical to sine theta by tan theta. Alright, so that the left hand side looks kind of bare bones, but I mean sec theta is 1 over cos, right? And that's cos theta over 1. And if we were to do simplification of fractions, I think cos theta would be the common denominator. Cos theta in itself is 1, and then 1 by the numerator. 1 will just give us back 1. 1 into cos theta goes cos theta times, multiplied by cos theta will give us cos squared theta. From above here, cos squared is equal to 1 minus sine squared. So we're doing 1 minus sine squared theta all over cos theta. So this is 1, sorry, what am I doing? Right, so that's 1 minus 1 plus sine squared theta all over cos theta. What's 1 minus 1? 0. So we're left with sine squared theta over cos theta. Right, so here's where the decomposing of the fractions will come in handy, because you might be wondering, well, how do we get, what is going on with this scrolling business? Alright, forget that. Yeah, how do we get back to here? Alright, so if we split apart sine squared into its components, we get sine multiplied by sine. Agreed? Alright, and that's all over cos theta. And we could pull apart that fraction, and put sine theta over 1 multiplied by sine theta over cos theta. And sine theta over cos theta will give us tan theta. All right. Okay. Any questions? Any problems? Or are we okay?
When you did the cos squared, I didn't do that. I just put
Mm-hmm.
sine squared. So I didn't put like
Okay.
1 minus open brackets 1 minus sine squared.
All right. So in other words, it jumped from here to here.
No.
Oh, all the way to the end. Okay. 1, 2, 3, 4, 5.
3. I did everything.
Uh-huh.
I reached 2, but then I read like
Mm-hmm. Oh, wait, yeah. I didn't have to do all that. Yeah, 1 minus cos squared is just sine squared.
yeah.
All right. Yeah, no, that would be way more efficient. Wow. Yeah, so you see, even when you're doing this years now, you can miss out something or take extra steps where extra steps are not necessary. All right. But yeah, good pickup. Okay. All right. So you all need some more time to progress from here, right? Okay, cool. So what I will do is I will also cut. Okay, so let's see if we can get back to this now. So we are at exercise, whoops, why did it disappear? All right, 7.4. Okay, so we stopped off at number 5. So we have for number 6 to do, right? Okay, cool. So let's go. So number 6 reads as follows. We have cot squared theta by 1 minus cos squared theta is identical to cos squared theta. So what this is essentially this is just going to cancel along to cos squared. Right, cot squared we know is 1 over tan squared, right? What's the other way we could write 1 over tan squared? Cos squared over sine squared. So we have cos squared theta over sine squared theta. Wow. Right, and again, worst boy. Okay, and 1 minus cos squared is sine squared, right? And guess what's going to happen here? Sine squared cancel with sine squared, giving us back cos squared theta. Are we okay with that one? Yeah? Shift this over. Okay, I think that'll be better. And go back this way. Alright, that could work. Right, number 7 now. Okay, we have 1 over cos squared theta minus 1 over cot squared theta, and that's identical to 1. All right, so at first glance you might think, okay, well, let's jump into the fractions. How many people jumped into the fractions? Nobody? All right, so you all took an alternative route, you all simplified it. What's 1 over cos squared? That's sec squared, right? Did you all go that route? Fractions? Okay, all right, let's take a look. Maybe I might just work it 2 ways just to see if there is a more efficient alternative, right? Okay, so sorry, before we do that, so 1 over cos squared theta. Now 1 over cot squared. Isn't cot squared 1 over tan squared? Therefore, if we have 1 over tan squared, guess what's going to happen? 1 over something will cancel, just giving us back tan squared, not so? Alright, so we have 1 over cos squared theta minus tan squared theta. Okay, and what's the alternative way to write tan squared theta? Sine squared theta over cos squared theta. Common denominator here is cos squared theta, which gives a numerator of 1 minus, sorry, I jumped any gun there, 1 minus sine squared theta, and 1 minus sine squared will give us what? Cos squared theta, and cos squared theta over itself will give us 1. Sorry, give me 1 second, let me see if I can do this. I just taken up some space here on the desk, right? All right. Okay, so 6 and 7, we okay with those? Yeah, all right, let's go down to 8 and 9. 8, we have a fun looking one, cot theta over tan theta plus 1 is identical to cosec squared theta. Now cosec we know is 1 over sine, so cosec squared is 1 over sine squared. So essentially what they're saying is that this should boil down to 1 over sine squared. All right, well that's one possibility. There are others. All right, so let's work on cot theta over tan theta, shall we? So cot theta over 1 multiplied by 1 over tan theta. All right, plus 1. All right, how else can we express cot theta? That's 1 over tan, right? So we could do 1 over tan theta multiplied by 1 over tan theta plus 1. And what's 1 over tan theta multiplied by itself? Anytime you multiply something by itself here, that's called squaring, right? So what are we going to get? 1 over tan squared, right? 1 over tan squared was cot squared, if I remember correctly. So we have cot squared plus 1. Aha! If we go back to our identities, 1 plus cot squared was cosec squared. So cot squared plus 1 is the same cosec squared. Yes? No? Maybe? Questions?
I forgot that.
Yeah. Did more work in. Yeah, don't worry. Like I said, the first time I went through this exercise, I didn't know about those two identities. So I took a longer time to work out those things.
Oh my gosh.
You see it?
Yeah.
All right. That's happened. Right? Remember, we train it now. And in the training, we'll make mistakes and see things we should have seen before. Right? That's the purpose of the training, to help us to see them beforehand. All right, so number 9, we have tan squared theta minus sine squared theta identical to, now we're going to sine to the 4th power and sec squared theta. So remember, sec is 1 over cos, so sec squared is 1 over cos squared. So you have sine to the 4th over cos squared. And if you split that apart, you get like a sine squared by a sine squared all over a cos squared, and sine squared over cos squared is tan squared. So we probably want to get to a sine squared by tan squared. Let's see if we get that. Well, how do we get that from tan squared minus sine squared, boy? So tan squared minus sine squared. So when in doubt, tan squared is what? Sine squared over cos squared, right? All right, so we're looking kind of good there. We have a sine squared and a sine squared that might end up as a cos squared. All right, so cos squared is the common denominator. So cos squared into cos squared goes 1. 1 by that numerator will give us back sine squared theta minus. Now 1 into cos squared will go cos squared times, and cos squared by sine squared will give us sine squared cos squared. So sine squared theta cos squared theta. Interesting. Now we have a couple of options here. One option is to factorize using sine squared theta as the common factor, which will give us 1 minus cos squared theta all over cos squared theta. Interesting. What's 1 minus cos squared? Aha! So we have sine squared theta multiplied by sine squared theta all over cos squared theta. And sine squared by sine squared will give us what? Sine to the 4th power over cos squared. And that's exactly what we wanted, isn't it? Sine to the 4th theta over 1 multiplied by 1 over cos squared theta. And that's sine to the 4th theta by sec squared. Yes? No? Maybe? Question? Anybody? Yeah. All right. All right. Well, that was pretty good, guys. You guys getting on some good ones there. All right. What's that face about?
I didn't get it.
Oh, you didn't get it? All right. What you did do?
I reached the part where you had the sine squared minus sine squared cos
Oh,
squared.
here?
Yeah.
All right.
I didn't factor.
Just in fact, that's what you did then. You expanded. Where did you put cos squared as 1 minus sine squared and expanded that? But it boiled along anyway, right?
Yeah, I didn't factor.
But you got the same result anyway.
I put tan squared.
Uh-huh.
I put sine squared over cos squared and then minus sine squared cos squared. I got confused.
Yeah, I think so. All right. Okay, but you see how to do it now, right? Right. And yes, sometimes when we get to stuff like this, because we're not accustomed dealing with and factorizing trigonometric terms, we're accustomed with the, like if it was x squared plus x squared y, we'll see the x squares very easily. And because we just accustomed focusing here. But now we have to kind of widen the view, all right? That's just how it evolves, guys, right? It's a learning process, and in that process you will make mistakes. That's okay. All right. Sine theta plus cos theta by tan theta plus cot theta is identical to sec theta plus cosec theta. Okay, I don't think we have much of a choice but to expand this using distributive law. Anybody else have any suggestions as to how we could work that otherwise? Well, I have an idea. Sine theta plus cos theta, currently we can't do much with that. But tan theta plus cos theta, we could actually modify that a little bit. Why? What is tan theta? Sine over cos. And was cot theta? Cos over sine. Right. So let's try this. Normally I would expand it using distributive law, to be honest, right? But let's see, right? Let's just consider this one first. So here we have why is my writing so horrible today? You know what? My writing is great. Sine theta over cos theta plus cos theta over sine theta. Okay, so if we do a common denominator, what are we going to get? We could just put, well, we could get sine theta cos theta, right? So cos theta into this will go sine theta times, and sine theta by sine theta will give us back what? Sine squared theta. And similarly, sine theta into that will give us cos theta. Cos by cos will give us back cos squared. Oops, didn't erase. And sine squared plus cos squared is 1, right? So we have 1 over sine theta cos theta. Now this could very well be going on the wrong path. It could be. All right? Because now what we have to do is we have to multiply sine theta plus cos theta has to be multiplied by 1 over sine theta cos theta. Okay, well that seems simple enough to do. I mean, if you multiply fractions together, you just multiply the numerators together and then the denominators together, not so? All right, let's see what happens. So sine theta plus cos theta multiplied by 1 will simply give us sine theta plus cos theta. And that's all over sine theta cos theta. All right. Remember how we said we have to know how to decompose fractions, how to split them apart? So check what we could do. We could do sine theta over sine theta cos theta plus cos theta over sine theta cos theta. And guess what happens? Sine will cancel with sine, giving us 1 over cos theta. Cos will cancel with cos across here, giving us 1 over sine theta. 1 over cos is what? Sec. And 1 over sine is? Cosec theta. Right. Now, I'm very sure I've never tried to solve it this way. I usually would expand it. So I get sine by tan, sine by cot, and then cos by tan, cos by cot. All right, you could do that. Anybody tried it that way? No? Oh, what did you guys do then? The same way?
I started off by doing it.
Okay.
And then I said this is all wrong and I erased it.
Yeah, trust me, when I was doing this back when I was in Form 4, Form 5, I would have had pages of work for this. All right, because same thing, you would doubt, you're like, how do I get from here to here? I'm not seeing my way. But sometimes, especially with this, it teaches you have to put one foot in front of the other and keep walking. That's all, sometimes. All right, okay. All right, I'm gonna hit that pause there and start back with the next set of stuff. So let's see. Boom. Okay, so this is once again exercise 7.4. So what number we got up to, guys? We stopped at 10 last time. Where we at? Alright, not bad. Alright, cool. Alright, cool. Okay, rest. So 11 was a bit of a tricky one. Why is my writing so horrible? 11. Right, cool. So this was sine to the 4th power theta minus cos to the 4th power theta identical to 1 minus 2 cos squared. Oh, everybody want a bark? No, what did you boy? Alright, what are you going to do? Okay, so like I was saying, you could use difference of two squares, right? So a squared minus b squared is equal to a plus b by a minus b. And the thing is, we know that a to the 4th power is equal to a squared squared. Sorry. Right, so we could actually simply turn this to a to the 4th minus b to the 4th and do a squared plus b squared and a squared minus b squared. So sine to the 4th minus cos to the 4th could simply become, so sine squared plus cos squared by sine squared minus cos squared. Oh geez, they real vex boy. Alright, so, and what's sine squared plus cos squared there? That's 1. So that entire bracket just kind of cancels out and we're left with what? Sine squared theta minus cos squared theta. Right, which just once again boils down to sine squared theta, that's not a square, wow, minus cos squared theta. And if we want to go just to here, it means we have to get rid of sine squared and express it in terms of cos squared somehow. What did I do? Okay, cool, thank you, right. Okay, so sine squared can be expressed as 1 minus cos squared theta, and minus cos squared will give us minus 2 cos squared. Are you okay with that? Yeah? Alright. Alright, number 12 now. So here we have cos theta plus sine theta all squared plus cos theta minus, sorry, why am I putting square inside of here? Erase no man. Alright. And that's identical, oops, to 2. So this has to boil down simply. So once you're seeing causes and sines and squareds, we should think cos squared plus sine squared is 1. But we know when we expand that first bracket, right, what's a plus b all squared? A plus b all squared is a squared plus 2ab plus b squared. And what's a minus b all squared? That's a squared minus 2ab plus b squared. So guess what's going to happen when you add these two things together? These will cancel out, right? Leaving us with 2a squared plus 2b squared. Well, let's see what happens here, right? So we're going to get cos squared theta plus 2 cos theta sine theta plus sine squared theta plus cos squared theta minus, right, 2 sine theta cos theta plus sine squared theta. So 2 cos sine minus 2 cos sine will cancel off. Cos squared plus sine squared is 1. Cos squared plus sine squared is 1. And 1 plus 1 is 2. Alright, so something that was looking all fierce and long working, boil long, real simple, real quick. Alright. Aha! 1 minus tan squared theta over cot squared theta minus 1 identical to tan squared theta. So you may wonder, well, how does this boil down? The trick here is to actually work with the denominator first, instead of trying to go and simplify the numerator using sine squared over cos squared. So check this, right? Cot squared theta is the same as 1 over tan squared, agreed? Right. Minus 1. So let's see if we could simplify some fractions there. So what's going to happen there? Common denominator here will give us what? Tan squared? Tan squared into tan squared goes 1. 1 by 1 is 1. Right? So we have 1. Minus 1 into tan squared goes tan squared times tan squared by 1 will give us back what? tan squared. So we have 1 minus tan squared. So our sum, our initial identity is now 1 minus tan squared theta over that. Of course, what's the understood operation between numerator and denominator in a fraction? Divide. So we could do 1 minus tan squared theta divided by 1 minus tan squared theta all over tan squared theta. And what's the protocol for when we are dividing with fractions? We change divide to multiply and do what? Invert the divisor. And look at that. The expression 1 minus tan squared cancels with itself, giving us tan squared theta. Alright. Yeah, don't worry. In the past, I probably went and worked the numerator as 1 minus sine squared over cos squared, and the denominator was cos squared over sine squared minus 1, and we had lovely things going on. Right? So, don't be afraid to try those things, but of course, it would be good if you could see the shorter, more efficient ways to work them. But that comes with time and practice and observation. I actually made up a little acronym recently. When you want to learn something, you had to teach it. You have to give it time. Time. You have to, in that time, you have to put effort and attention. You have to be consistent in those things, and you have to help other people. Teach. Yeah. All right, so number 14 now. All right. Sec theta plus tan theta is identical to 1. All right, this resembles one that came, I think, in the 2012 paper. All right, so let's start with this side. So sec is 1 over cos, right? Tan theta is sine over cos, yeah? So common denominator would simply be cos theta, yeah? Numerator would be 1 plus sine. Now, from here you must be wondering, well, what the hell? All right, where are we supposed to go from this? This requires a very specific application. You all remember surds, right? And how to rationalize the denominator, and it required you multiplying by whatever would make the denominator difference of 2 squares. Well, here we can't make the denominator difference of 2 squares, but we can make the numerator difference of 2 squares by multiplying by its conjugate. Yes, it was not entirely obvious. This was the bad one. All right. So 1 plus sine theta by 1 minus sine theta will give us 1 minus sine squared theta in the numerator over cos theta by 1 minus sine theta. All right. Actually, hold on, wait. That's how I'm supposed to work this? Just now. All right, let's go. Let's just see where it carries us, right? Because I'm now thinking it might have been. We may have whatever. We might have had to have. I can't even English now. Instead of multiplying by 1 minus sine theta over itself, it might have. Why can I not finish this sentence? I honestly don't know what's going on. So instead of this, it should have been cos theta over cos theta. But let's just see what happens, right? So 1 minus sine squared is cos squared, right? So cos squared theta over cos theta by 1 minus sine theta. Yeah, I don't see this going anywhere productive. Hold on. Can this not cancel with that? So what will you get? Cos theta over 1 minus sine theta. Right. Remember I had something called a double inversion I was telling you about? Now there is probably an easier way to work this, to be honest, but this is just what's happening today, right? So what's going to happen here, you're going to have 1 minus sine theta over cos theta. And guess what's going to happen? We could decompose that fraction, right? And 1 over cos theta is, and sine theta over cos theta is tan theta. Yeah, that one was a bit of a pain. It was fun, but a bit of a pain.
I've never gotten that.
I know. Yeah. If, like I said, there probably has to be an easier way to work that. Most likely we could try multiplying by cos over cos instead. Because you get cos squared, which could be 1 minus sine squared, which could then do difference of 2 squares. Yeah, that might have been the better way to go. Alright. What is all that? Don't even know. Alright guys, let me see if I can hustle down 15 and say, I definitely want to show you all 16 because normally I would expand 16. But I have an idea with 16. Alright. 15. So we have sec to the 4 theta minus sec squared theta is identical to tan squared theta plus tan to the 4 theta. Alright, so hold on. Remember there was one that said tan squared plus 1 is sec squared? Alright, if anybody's wondering why I'm scratching the screen, it's supposed to erase like that. There you go. Alright, sec to the 4 minus sec squared. We could factorize sec squared theta into sec squared theta minus 1. So look at that. If we carry that across there, what do we get? Sec squared theta minus 1, right? So the sec squared on the outside could become tan squared plus 1. Right? That's on the outside. The bracket on the inside will become tan squared. And when you expand that, guess what happens? Tan squared by tan squared is tan to the 4 theta, and tan squared by 1 is tan squared theta. One line. Right? Alright, so the first thing I did was to factorize with sec squared. Right? So in doing that, I got sec squared minus 1 on the inside and sec squared on the outside, right? Then using this identity, right? So the sec squared on the outside could simplify to tan squared plus 1, right? This on the inside, so you could do tan squared plus 1 and then you have to minus the 1 from that. So you're just going to get tan squared on the inside. Alright? And 1 for the road, is it 35? Oops. Alright. Okay, so this one, I used to do all kind of madness for this to try to work this out. I used to have it was a double inversion. It was factorized with minus 1 in the numerator and denominator. Let's see if I can work this out even more simply. Alright, cosec is 1 over sine, right? One cubic, give me a rest now, man. Cot is cos over sine, right? And if we simplify the fraction on the inside, there's a common denominator, is there not? Sine theta. Now, when we square a fraction, well, when you square anything, you multiply by itself. When you multiply that by itself, you get 1 minus cos theta all squared all over sine squared theta, right? Not sine cubed, sine squared. Now, before you expand that numerator, watch this, right? 1 minus cos all squared could be written as this. Agreed? 1 minus cos by itself. Your denominator, which is sine squared, could be written as 1 minus cos squared. And that denominator can be seen as the difference of 2 squares. Isn't 1 the square of itself? And isn't cos squared a square? So this could be a plus b multiplied by a minus b. Boom, boom. All right.